paper we will discuss today is the overview of the SPARC tokamak. Chapter 3, Machine Parameters and Cross-Section. The SPARC V2 design described in this article is the result of an interactive process that consisted of analyses of many different aspects of plasma physics and engineering design. The engineering design of SPARC is not the focus of this article, so only general descriptions of the various engineering systems are given. The measure parameters of the SPARC tokamak are given in Table 1 with a measure radius of 1.85 meter and an inverse aspect ratio of 0.31. SPARC is similar in size and aspect ratio to many present-day medium-size tokamak such as D3D, ASDX, Upgrade, East, and K-Star. A much higher toroidal field, however, allows for a larger plasma current at the same safety factor and significantly higher triple product than is possible in present devices. Figure 2 shows the toroidal cross-section of SPARC V2. The entire SPARC device is up-down symmetric to the maximum degree possible, enabling test of symmetric double null operation. SPARC's central solenoid consists of a total of 3 pairs of HTS upper and lower coils, labeled CS1, CS2, and CS3. The machine has 4 upper-lower pairs of HTS toroidal field coils outside of the toroidal field coils, labeled PF1 to PF4, moving outward in measure radius. In addition, there are 2 pairs of copper coils that are internal to the toroidal field coils, but external to the vacuum vessel. Since these coils are primarily used to actuate the diverter magnetic field, they are labeled div1 and div2, upper and lower. There is also a pair of vertical stability coils inside of the vacuum vessel, labeled VS1 upper and lower. Finally, there are 3 sets of picture frame error field collection coils, 1 upper, 1 lower, and 1 mid-plane. The vacuum vessel is double-walled, with space in between the walls for gas heating and cooling of the vessel. Roughly half of the space between the vacuum vessel walls, as well as the space between the vacuum vessel and the toroidal field coils, is filled with neutron shielding material in order to reduce the nuclear heating of the superconducting magnets. The vacuum vessel has 3 ports at each toroidal location, 1 mid-plane port and a symmetric pair of mid-plane ports above and below. The diverter is toroidally continuous and tightly baffled to contain neutral particles in the diverter volume. Both carbon and tungsten are currently under consideration as the material for plasma-facing component. This trade-off is described in detail in Kuang et al. And to a lesser extent in Sweeney et al. But in short, carbon plasma-facing components would result in lower core impurity radiation and more forgiving diverter operation relative to tungsten, but would also result in increased tritium retention due to higher rates of erosion and CO deposition, while tungsten-based plasma-facing components are thought to better project to a power plant. The relatively short integrated plasma time in SPARC means that carbon is an option as a plasma-facing material, and so both materials are being examined upper or lower passive stability plates are located between the vacuum vessel and the plasma to improve vertical stability and allow operation at high elongation. SPARC has 18 toroidal field coils in an attempt to balance the competing constraints of minimizing magnetic field ripple and maximizing vacuum vessel port widths. It is being designed to have up to 25 MW of 120 MHz ion cyclotron resonance heating ICRH coupled into the plasma as the sole source of auxiliary heating. The central solenoid and toroidal field coils set will be capable of producing 42 Weber of magnetic flux to initiate and drive the plasma current with a plasma flat top time of 10 seconds, and all systems are being designed to support full power operation for a 10-second flat top. As is described further in Chapter 4, the compact size of SPARC allows it to achieve a well-equilibrated plasma in terms of energy confinement and magnetic equilibrium in a relatively short discharge, smaller than 10 seconds, compared to a larger machine like ITER. Easing the design of many engineering systems, SPARC's predicted energy confinement time is T equals 0.77 seconds. See Chapter 4 for details of this calculation, such that the flat top encompasses more than 10 energy confinement times. Figure 3 shows representative plasma current and safety factor traces as calculated with tokamak simulation called TSC. For the full performance SPARC discharge described in more detail in Chapter 4, as this figure shows, the current profile is well equilibrated within approximately 5 seconds of the beginning of flat top, and after this point changes to the Q profile due to short teeth dominate any additional relaxation. This result is consistent with more detailed time-dependent transport simulation described in Rodriguez Fernandez et al. The iterations of the SPARC design that led to V2 incorporated a wide variety of engineering analysis, as the toroidal field coils are perhaps the most novel aspect of the SPARC design. Considerable effort has been dedicated to their structural, thermal, and electromagnetic analysis. Similar efforts have been made for the central solenoid and toroidal field coils. The vacuum vessel has also been a key focus of the early design work, as it interfaces with many other systems, and most withstand large disruption loading since ICRH is the only external heating source. Its design has also progressed considerably in order to ensure that it will be able to reliably couple the necessary amount of power to the plasma. In addition, the efforts of neutron heating have been modeled for the entire device, including determining the requirements for cooling of the superconducting magnets during DT operation. The high volume, average fusion power density, and tight radial build of SPARC means that volumetric neutron heating of various components is of particular importance. Thought, as stated above, detailed engineering analysis is beyond the scope of the work presented here. Thank you for listening to the end of today's show.